In 1986, India initiated the Cavalry project to build a domestic propulsion system for its light combat aircraft. After decades of development, the engine was eventually delinked from the Tejas fighter jet program. The Tejas requires an engine capable of 81 kilonewtons of thrust within a very specific weight envelope. Early Cavalry prototypes reached approximately 75 kilonewtons, but the hardware was consistently heavier than the airframe could accommodate. This chart compares the project's total funding to established international benchmarks. The Cavari project operated on $239 million. By comparison, the General Electric F404 development cost over $1 billion, and the Pratt and Whitney F-135 reached $6.7 billion. Following India's nuclear tests in 1998, international sanctions severed the country's access to vital aerospace technology. Researchers were suddenly blocked from importing critical components and classified materials, forcing them to develop internal solutions for every technical hurdle. A working jet engine requires an established ecosystem of test beds, metallurgical labs, and precision manufacturing. Because these did not exist in India at the time, the project had to establish the industrial infrastructure to produce the engine while simultaneously attempting the design. The resources spent on the early project resulted in type-certified alloys, domestic component test facilities, and a workforce trained in a discipline where India previously had zero presence. In the 1990s, jet engine development relied on physical hardware trials. Engineers would machine a component, push it to failure on a test stand, and analyze the wreckage to begin the next design cycle. Today, the gas turbine research establishment utilizes high-performance computing and product lifecycle management frameworks. Using high-fidelity computational fluid dynamics and digital twins, engineers now test thousands of virtual iterations before a single part is cast in metal. Efficient jet propulsion requires extreme internal temperatures to maximize thrust. To push past previous performance limits, engineers must subject turbine components to conditions that would melt standard industrial alloys. Traditional turbine blades contain microscopic grain boundaries, structural weak points where cracking begins under intense engine stress. By 2021, the Defense Metallurgical Research Laboratory eliminated these boundaries. Using a controlled vacuum furnace, they created single crystal turbine blades with one uniform metallic structure. These single crystal blades allow the engine to operate at temperatures up to 1500 degrees Celsius. This capability directly addresses the overheating and material deformation issues that limited the original Kaveri prototypes. Because the metallurgy and manufacturing processes have changed, the modern engine is no longer tied to the material constraints of the 1980s. This is the dry Cavalry. It is a derivative that retains 75% of the original design features, but removes the afterburner section to focus on subsonic performance. Manned fighter aircraft require afterburners for the supersonic bursts used in combat. However, stealth drones prioritize a different set of requirements, focusing on fuel efficiency and a minimal detectable signature. The lack of an afterburner reduces the engine's infrared signature, making the aircraft harder for thermal sensors to detect. With approximately 50 kilonewtons of thrust, the dry Cavalry is optimized for the 13-ton Gatic Stealth UCAV, providing the efficiency needed for deep penetration missions. High-altitude flight trials in Russia are currently in the final stages, with certification for the engine targeted for 2026. Repurposing the engine for unmanned aviation allowed the project to match the hardware-specific capabilities with a platform that prioritizes stealth and endurance over supersonic thrust. Developing the dry Cavalry provides a technical bridge toward a 110 kilonewton class engine intended for the advanced medium combat aircraft, India's next-generation stealth fighter. Owning the intellectual property for single crystal blades and the Kabini Corps changes the nature of future partnerships. Ongoing discussions with Francis Saffron are now informed by India's existing industrial base and proven hardware. A domestic engine capability ensures the operational continuity of air assets during a conflict. It allows India to maintain its fleet independently of foreign export controls or shifting geopolitical alliances. Global aerospace companies required decades of iterative design and massive institutional support to refine their modern propulsion systems. The Cavari project has established a permanent industrial ecosystem, ensuring that India's future aerospace development is supported by a foundation of indigenous expertise.